So now that we have more of you here, so I posted the rest of the homework on the website, and I made some very small changes to the questions that I had posted originally. So you should read the new version, and that's the one. Okay. So today we're going to count. That's what we're going to do. We have been talking about parabolic subgroups, parabolic quotients, and today I want to talk about an enumerative application of these ideas. Length generating functions. I'll tell you what that means. I would like to count in a Coxeter group. For example, here's the Bruhat order for S3. And one thing that I would like to know, for example, is how many elements a Coxeter group has. But I want to know more than that. What I would like to know is not only how many elements there are, but how many there are at each level. Okay? And so what I'm going to do is basically encode this information in a polynomial. So by saying there's 1 in this level, 2 in this level, 2 in this level, 1 in this level, I'm going to encode those numbers in a polynomial, which I denote S3 of Q. And these numbers are just going to be the coefficients. So 1 plus 2Q plus 2Q squared plus Q cubed. Okay. So in general, I'm going to make a polynomial. This might be a polynomial, or actually it would be infinite if the group is infinite. Right? But what I'm going to do is sum over all the elements of my Coxeter group, Q to the length of the element. So in this case, this would give me Q to the 0 plus Q to the 1 plus Q to the 1 plus Q squared plus Q squared plus Q cubed. And so basically, if I can compute this function, then I know exactly how many elements there are in each rank. Okay? So this is called the length generating function, or you might also call it the Poincare. Now, this is either a polynomial or a series. In general, it's a series, because in general, Coxeter groups can be infinite. In this case, it's a polynomial. Okay. So, for example, what about the next one? So I think some of you have pictures of S4 in your notebook. So why don't you tell me what the numbers are for S4? So S4 of Q is equal to 1 in the bottom level, 3, 5, 6, 5, 3, 1. So if you're doing the homework and you're going to draw S4, you should double check that you do have this number of elements in each rank. And if you don't, then you should double check your work. This is the correct answer. And there's a first thing that you notice about this and about this, which is that these polynomials are palindromic. Okay? And this is where we would like to say, okay, what can we actually say about these polynomials? And for example, that's a theorem. If W is finite, then W of Q is palindromic. Now, palindromic means that the coefficients are the same from left to right. Now, let me write this in a fancy way by saying, if I plug in 1 over Q, I get this. So you should think about why if I plug in 1 over q, basically what I'm doing is just reversing this polynomial. Okay? So saying that it's palindromic is equivalent to saying this thing. So this is not only true for S3 and S4, it's true for any Coxeter group that's finite. And actually the proof is very simple once you know what to do. Because the thing is that we have an operation that takes this post-it and flips it upside down. And that is the operation of multiplying by the longest element. Yeah, then the map that takes W to W naught, we said that's a post-it anti-automorphism. Anti-automorphism, that's a long word, but it basically means that multiplying by W naught just flips the post-it around and makes it look the same way. When you multiply by W naught, the things that have rank k from the bottom end up having rank k from the top. Okay? For example, multiplying by W naught sends these 5 guys of rank 2 to these 5 guys of rank 4. And that's why this is palindromic. So the reason is very easy. And sends elements of rank k to elements of rank length of W naught minus k. So that's the proof. Okay. So that's the first observation. But maybe we're not satisfied with this. Maybe we actually want an explicit formula for this. I think we shouldn't settle for so little. So for example, what's the Poincare polynomial for the symmetric group? That's a nice, reasonable question. And so what I would like to do is answer that question. Okay? Now, before I get to that, let me point out a lemma to you. The lemma is that the Poincare polynomial, or series, of W is equal to the Poincare series of W super J times the Poincare series of W sub J. Where when I write this, I mean exactly the same thing. It's the same polynomial, except that instead of adding over all of W, you add over the elements in W super J here, the elements in W sub J here. Okay. So why is this true? Well, you can imagine that this is true because we have this way of factoring elements of W as something here times something here. And that's the proof. So let's go ahead and write that down. So this is the definition of the Poincare series. But now I know that I can factor each W as a W super J times a W sub J in a unique way. Okay? And so basically, take it a little slowly. So I can factor W as W super J, W sub J, okay? But remember that one property of this factorization is that the length of W is equal to the length of this part plus the length of this part. We proved that. And so let me rewrite it in this way. Okay. Now, I'm saying something stronger than this because every W can be written as W super J times W sub J, and every product W super J times W sub J gives me a W. That's a correspondence. And so instead of summing over all the W's, which are in my Coxeter group, I can add over all pairs of a W super J in W super J and a W sub J in W sub J. So let me rewrite it like that. I add up over all of these guys, and I add up over all of these guys. Okay. And then basically I just separate these sums. I separate it like this and like this. Okay. If I multiply this sum times this sum, then when I distribute, I'm going to get exactly this double sum. Okay. And that's it. This is W super j, and this is W sub j. So really, there's nothing here except kind of working through the notation and making sure that you understand the notation, but it's a pretty straightforward lemma. Yep.
Just brackets around your series.
They're just brackets like parentheses. Yeah. They don't mean anything special. Okay. Okay. Now, why is it that this lemma is so powerful? Because my goal for today is to compute this series W of Q, right? The Poincare series of a Coxeter group. Now this is telling me that I can compute the Poincare series of my Coxeter group if I'm able to compute these two things. Now what is this thing on the right? Well, W sub j is another Coxeter group. We proved that. And so this reduces the computation of this Coxeter group to a smaller Coxeter group, and this thing, which is not a Coxeter group. But the point is that if I'm able to compute this guy, then I can recursively compute this guy using this guy. So that's my plan. And so the way I'm going to do it for the symmetric group. So what does this say for the symmetric group? Well, it says that this. Okay. And actually, this is true for any j, for any subset of the generators. Okay. So I can choose which j I would like to plug in here. Okay. And now I'm thinking that I'm going to compute this recursively. And so you're going to see that a convenient choice of j is basically that we know that the graph, the Coxeter graph of this thing looks like this. Right? So this is S1, S2, up to Sn minus 2, Sn minus 1. And what I would like to do is take j to be equal to everything except for the last guy. Okay. I would like this to be j. And the reason for doing that is that if I take that to be j, then what is Sn sub j? Well, it's the group generated by S1, S2, up to Sn minus 2 with Coxeter relation. So that's just the one smaller symmetric group. Okay. So if I take j to be equal to this thing, so j equals S1 up to Sn minus 2. If I do that, then I'm left with this times this is just the symmetric group Sn minus 1, basically. Okay. And so that tells me that I'll be able to compute the Poincare series of the symmetric group as soon as I'm able to compute this polynomial Sn super j of Q. And then I will just get it by induction. Okay. Any questions so far? Okay. So let's compute this then. What is Sn super j? Well, we have to remind ourselves what the definition is. These are the elements that cannot be reduced by right multiplication by j. And we said that that's equivalent to saying that no reduced expression can end with j. So if you have something that no reduced expression can end in S1 and S2 up to Sn minus 2, that means that the reduced expression must end in Sn minus 1. And so these are the permutations whose reduced words must end in Sn minus 1. Okay? What do these things look like? I mean, is this a common property? Is this a rare property? Well, let's just try to make a list of some of them. For example, of length 1, of length 0. So of length 0, of course, the only thing that I can make is E, right? The identity. The identity is in any of these guys. Okay. Now, what things of length 1 can I have here? Well, they have to end in Sn minus 1, so the only choice is Sn minus 1, the transposition of n minus 1 and n. That's the only element of length 1. What are the elements of length 2? Well, if they're of length 2, then I must be able to write them as something times Sn minus 1. Right? But what can go here? Well, Sn minus 1 cannot go here because this would not be reduced. Sn minus 2 could go here. Could Sn minus 3 go here? Actually, it couldn't. And the reason is that Sn minus 3 and Sn minus 1 commute. And if they commute, then I can switch them and make a word that doesn't end in Sn minus 1. And the same is true for Sn minus 4, S everything. The only generator that doesn't commute with Sn minus 1 is Sn minus 2. So that's the only one that I can put here. So this is the only thing that I have of length 2. Let's try that again. What about length 3? Well, they have to look like this times Sn minus 1. What can I put here? Well, I saw that the only thing I can put there is Sn minus 2. And what can I put here? Well, again, anything that's less than Sn minus 3 is going to commute with both of these guys, so I can send it through. So this must be Sn minus 2 or Sn minus 1. Or Sn minus 3, sorry. Now, it can't be Sn minus 2 because this wouldn't be reduced. Can it be Sn minus 1? No, because I would have a braid relation. Sn minus 1, Sn minus 2, Sn minus 1. I could switch that to Sn minus 2, Sn minus 1, Sn minus 2. So it can't be that either. So this must be Sn minus 3. Okay. You see the pattern. And it turns out that these are the only things. I mean, if you continue making this argument, you're going to see that the only possible guys that you can get are S something plus 1 up to Sn minus 1. Exactly. So what does this look like as a poset? Well, it has one guy in each rank. E, Sn minus 1, Sn minus 2, Sn minus 1, Sn minus 3, Sn minus 2, Sn minus 1. It's just a chain. So that means that what is the Poincare series of this guy? Well, I have one guy in each rank. Where should I stop? Q to the what? Well, the last guy that I will see here is S1, S2, S3 up to Sn minus 1, which has length n minus 1. So I should stop here. Okay. And so you see actually the computation of Sn super j is very easy once you understand what Sn super j means. And so what this is saying is that to obtain Sn of Q, the Hilbert series for the symmetric group, you just go to the previous symmetric group and you multiply by this thing. Okay. So let's see that in action here. Well, first of all, what is S2 of Q? This 2 of q is just having a single generator, so the elements are either the identity or the generator. What's S1 of q? It's 1. Now, if you look at this factors as 1 plus q times 1 plus q plus q squared. And you can check that by either multiplying this out or by resorting to this theorem that says that this guy is obtained from this guy by multiplying by this. Now, to get from here to here, all I have to do is multiply by 1 plus q squared plus q cubed, and so on. So I've proved I have my formula. Theorem. Formula for Sn of q is just 1 times 1 plus q times 1 plus q squared, etc., up until 1 plus q plus q to the n minus 1. That's it. As beautiful a formula as you might hope for. Now, why does the symmetric group have n factorial elements now? Because if you would like to count all the elements of the poset, you just add up all the coefficients, and the way you do that is by plugging in q equals 1. And if you plug in q equals 1, you're going to get 1 times, that's why I put the 1 here, 1 times 2 times 3 times n. It's a very convoluted proof that there are n factorial permutations of n elements. Beautiful theorem. Very nice. I should tell you that people like to write this in this way as people call this the integers 2 sub q, 3 sub q, until n minus 1 sub q, and people like to call this this is nq, sorry. People like to call this n sub q factorial. Okay, where I sub q is just this, 1 plus q up to q to the I minus 1. So if you ever see this notation, that's what it means. This is called these are called the q analogs of the integers. These are like the integers except that you have a parameter q. And so basically this is just the q analog of n factorial. Okay, so that's the nicest formula that we could hope for the symmetric group. And that begs the question, okay, what about the other groups? Yeah. Is it always this nice? Well, let me just state something that is pretty easy to prove, which is that if you have a Coxeter group, which factors? Now remember, when does this happen? If I give you a Coxeter diagram and the Coxeter diagram has separate pieces, then we know that the Coxeter group of the whole diagram is equal to the product of the individual Coxeter groups of the pieces. Now, if you have a factorization like this, then what do you think happens to the Poincare series? Well, hopefully the easiest thing happens, and it does happen. You just multiply them. This is an easy exercise, actually. Just have to kind of go through the definitions, and you'll see that there's nothing much to say there. So what this tells us is that if we would like to compute the Poincare series of Coxeter groups, then we might as well restrict our attention to the ones that have connected graphs. Because for disconnected graphs, we just multiply these guys. Okay. So what about connected graphs? Here's a theorem. Let's say that we have a Coxeter system which is finite and irreducible, where by irreducible I mean exactly this, that it can't be factored into smaller things. Let's say that there are n generators. Then there is a formula of the form W of Q is equal to something like this. Okay, so there exist natural numbers E1 up to En such that this Poincare series factors in exactly the same way as that one over there. Okay. So this one is 1 sub q times 2 sub q times 3 sub q up to n sub q. If you pick any other finite Coxeter group and you compute its Hilbert series, then these numbers are going to change, 1, 2, 3 up to n, but the form of the formula is not going to change at all. It's just a product of q analogs of integers. This is an amazing theorem.
Sorry, is 0 the natural number in our world? Yeah.
0 is a natural number in my world. Yeah. So it depends whether you're in, I think, whether you're in the US or in Europe.
And it has the same formula. That can't be right. You need that term to.
Well, the only difference whether you allow 0 or not is whether you allow a factor of 1 sub q, but 1 sub q is 1. So it really doesn't make a difference. But actually it does make a difference because I want to have n of them. And so I guess I don't want 1 because here I have n minus 1 generators, so really I want this to be a product of n minus 1 things. So I guess what I want is this. Same thing, technicalities. Okay. Now, for example, what does this mean? Remember I told you last time that if you wanted to know the number of elements of a Coxeter group, that always factored very nicely. Well, what's the number of elements of this Coxeter group? Well, we know that if we have the length generating function that counts according to the levels, and if I don't care about the levels, then I just plug in q equals 1. And then all of a sudden, I'm just adding up all the numbers in each level. So if I want to know the number of elements of my Coxeter group, I just plug in q equals 1. And for q equals 1, I sub q is just I. And so what I get is just the product of E1 plus 1 up to En plus 1. And so this is why I was telling you these numbers always factor very nicely. Okay. And for example, if I would like to know what's the height of the post-it, what's the length of the longest word, where basically I have to figure out what's the degree of the polynomial. Yeah. Now, this polynomial has degree E1, E2 up to En. So the total degree of the polynomial is the sum of the EIs. Okay. And so that means that if you manage to compute these EIs, then you know very nice enumerative information. Okay. I should tell you there's a name for these guys. You can imagine, I mean, this theorem tells you that these numbers are very important. They play a very important role for the Coxeter group. I think this red is not going to show up in the film. These are called the exponents of the Coxeter group. So this is the beautiful theorem telling you about the enumeration of finite Coxeter groups. Every finite Coxeter group has a very nice Poincare series. Okay. Any questions about this statement? Now, the proof there's a few ways of doing this, and we're not quite ready to do either one. But I feel like once I've stated this, I have to tell you this beautiful theorem. There's a really very nice conceptual way of proving this, which is via something called invariant theory. There's one proof. It's via something called invariant theory. Let me tell you very quickly what that's about. Invariant theory is about letting your group act on a space of polynomials. Okay. So for example, how does the symmetric group act on a space of polynomials? Well, one way of doing it is if you consider polynomials in 3 variables x, y, and z, then you can multiply permutation by a polynomial by saying that the permutation just mixes up the order of the letters. Okay. And so invariant theory studies that kind of action of a symmetric group on a nice ring. And then through some algebraic machinery, you get this to come out. Okay. This is a beautiful subject that I won't get to say very much about in this class. Very nice topic for a project, actually, if you want to learn about the invariant theory of Coxeter groups. And I'll be happy to point you to references and help you with that. Now, there's something a little bit funny about proving theorems about finite Coxeter groups. And the funny thing about that is that actually there's a complete list of which ones are the finite Coxeter groups. And that's something that we will prove, but I haven't proved to you yet. But there is a complete list. And basically, what are the finite Coxeter groups? Well, here's one that's always finite, right? Any segment like this, that's always finite. These are called the AN groups. Then there's some that look like this, except you have a 4 here. Those are also finite, and they're the hyperoctahedral groups. There's other ones that look like this. So when you have a diagram like this is always finite. And there's a finite list of them. Okay? There's another one that looks like this, and like this. And so basically, once you have the complete list, then basically this statement is a statement that only refers to this finite list of examples. And so one way of proving a theorem like this is, well, you prove it for permutations, you prove it for sign permutations, you prove it for each one of these things. And that's one way of doing it. Case by case. Okay, but that depends on this classification of finite Coxeter groups, which we will do, but I haven't done yet. But so maybe that's all I'll say about this, is that there is a very nice formula for finite Coxeter groups. And in particular, there are tables, and you can look up this table in the book. For each one of the finite groups, there is a list of exponents. Yeah? So for the symmetric group, their exponents are 2, 3, up to n, and there's just different exponents for each one. But so that means that you get a complete list of all the Poincare series for all the finite Coxeter groups. Okay. So how do you deal with infinite ones then? So here's a theorem. Here's a theorem that allows you to compute the Hilbert series for any Coxeter group. So you start with some Coxeter group W comma S, Coxeter system. So let me first write the formula, and then I'll tell you how to use it to compute. If you add up over all subsets of generators, and for each one of them, you do this. When you do this, you get something very simple. You get 0 if W is infinite, or you get Q to the length of W naught divided by W of Q if W is finite. So let's parse this and see what this is actually saying. This is an equation that relates for all the different subsets of S, the generating functions for all the different parabolic subgroups. Okay? And so if you want to compute the Hilbert series of a particular group, this formula reduces it to the computation of all of its parabolic subgroups. Yeah?
Do you mean Poincare series, or are they the same? I sometimes.
So I'm saying Poincare series, and I'm saying generating function.
No, but you said Hilbert series.
And when I say Hilbert series, it's a mistake. But whenever I say something that sounds like a series, I'm talking about the Poincare series. Okay. Thank you for correcting me. Poincare series. Let's see how you do this in an example. So what's the smallest infinite Coxeter group that you know? This one, right? You proved that in the homework that this is the group of order-preserving symmetries of the orientation-preserving symmetries of the triangular grid, and there's infinitely many of them. Actually, you know a simpler one, by the way. So this is an infinite Coxeter group, but this one is too boring. Let's do this one, which is more not too boring, but this one's more interesting. So let's see how this works out. So what I'm claiming is that this theorem is going to allow me to compute the Hilbert series of this infinite thing by reducing it to its subgroups. Okay? So if I'm claiming that, the first thing I should do is compute the Hilbert series of the subgroups. So for example, what are some of the subgroups? Well, one of the parabolic subgroups is the one generated by nothing. So what's the Poincare series of that one? That's the hardest, actually. So we'll wait. What's the Poincare series of the one generated only by A? You have only one generator, so it's either the identity or A. So it's 1 plus Q. And by the way, it's the same for B or C, right? This is the same for A or for B or for C. Okay. Now, what about the one for A comma B? What's this Poincare series? Well, I cover this up, and then this looks like a symmetric group. And I already computed what this is. This is 1 plus Q times 1 plus Q squared. And the same is true for AC and for BC. What about this empty one? It's just the identity, right? There's nothing generating, so it's just the identity, and so you just get a 1. Okay. So now what is this formula saying?
Do we also take the entire set?
So right, so what about the entire set? Well, the thing is that that's exactly what I don't know how to compute. Right? And so what I'm claiming is that this formula expresses this one in terms of these, and that's how I'm going to compute it. So let's actually write out this formula.
So that should be a strict subset, right?
Yeah, it shouldn't be.
No,
The J.
no. This is a. Let's see how it works.
The generator
Yeah.
sometimes.
So I have to do it for all the subsets. So for empty, for 1, for 2, for 3, for 1, 2, for 1, 3, 2, 3, and 1, 2, 3. So for the empty set, I get minus 1 over, no, I get plus 1 over W sub empty of Q. Then here I get, sorry, these are letters, right? A, B, C, A, B, A, C, B, C, A, B, C. So for this one, I get minus 1 over W sub A of Q, and the same for B, and the same for C. Then I get plus 1 over W sub A comma B of Q, and the same for AC, same for BC. Then I get minus 1 over W sub A BC of Q. And what this theorem says is that when I add these 8 things together, I get 0 because this is an infinite group. Okay. So let's go ahead and do that. This guy is 1. Then these 3 guys are equal to each other. So I get 3 of them, and each one is 1 plus Q. Okay. These 3 guys. These 3 guys are also all equal to each other. So I get plus 3 divided by 1 plus Q times 1 plus Q squared. Okay. And then mystery guy, right? This is the one that I don't know. And so that's how you do it. Then that expresses W of Q in terms of the other ones. You just solve for W of Q. I'll tell you what you get. You get 1 plus 2Q plus 2Q squared plus Q cubed divided by 1 minus Q minus Q squared plus Q cubed. That's what you get when you solve all of this stuff. This factors nicely, by the way. So this is 1 plus Q plus Q squared. And I guess this is what? 1 minus Q. Actually, there's even a factor here, right? I think you just get this. Yeah. You just simplify and you get that. Now, there's something you should notice here, which is that for finite groups, our series read the same, our polynomials read the same forward and backward. And if you look at this, this also reads the same forward and backward. And that's no accident. That's a theorem. So I wish that I hadn't erased the other theorem, because exactly the same thing is true here. So there's a proposition, which is that if W is infinite, then basically, I mean, the series is not exactly palindromic, because it goes to infinity in that direction, and it doesn't go to infinity in that direction. But it's basically palindromic in that when you write it as a rational function, the pieces are palindromic. So let me write in quotations palindromic as a rational function. And what I mean exactly is that if you plug in 1 over Q, you basically get the same thing as if you plug in Q, except you might be off by a sign. This might look familiar. This is a homework problem. Now, I know, John, that you asked me how on earth to get started with this because I hadn't told you guys anything, but now you actually have some tools to at least understand what this question is saying and how you can get started to prove something like this. And I think maybe I won't rush through the proof of that, so maybe we'll just prove it next time. And that means we have some minutes for questions if you have any.
So you kept calling this thing a Hilbert series. What's the Hilbert series of?
I was calling it a Hilbert series by accident because I think more about Hilbert series than about Poincare series, but really, a lot of the times they're the same thing. So Aaron's question is, why can't I call this a Hilbert series? This probably is the Hilbert series of some graded ring. And if I remember correctly, that's exactly this. But yeah, I'm pretty sure that basically it's a Hilbert. It's the Hilbert series for the invariant ring that determined by the group.
Did Poincare actually have something to do with this?
Did whom?
Poincare.
Not with this, no.
So it was named in honor of him, but not directly.
I'm honestly not sure. I mean, these things are often called Poincare series, and I don't think he was thinking specifically about Coxeter groups.
Yeah,
but
no, they were invented meant much. But
yeah.
Maybe he did a computation or something that
Yeah.
involved something.
Yeah, I'm honestly not sure where the name Poincare series comes from. Yeah. Okay. We also have office hours now, so we can morph this into office hours.
You're not going to talk about bio right here?
A little bit because they come up in the classification as finite Coxeter groups. But I won't talk about the connection with the algebra.
And so like series, it has quite a few with the system. I might fix that out. So would you be
I got here today, I didn't realize, because I left early this morning. I think it's stuff done before school. I realized I brought everything for breakfast, and I brought a portion of my lunch. I didn't bring the most important part. I'm eating an orange. Yeah.
I can show you a book. So it's basically called Reflection Groups and Invariance Theory. And it's a very nicely written book, and it tells the story and it goes through.
Is it the one the Canadian?
Yeah.
So that is what's Kane? Okay, I have it. That's not
So
and what about positives? I mean, the definite, what's the definiteness? I thought one of the things that you recommend.
I'm going to hopefully extract information.
yeah. I mean, the book of Kane and the book of Humphreys both
I'm
talk
not
about this
sure
quite a bit.
quite yet, but
So one thing you could do is kind of flip through it and see what section was interesting to you.
well,
But then
the thing is, I feel like I'm wasting time
that
if I don't see him.
I mean,
Just to have office hours. Yeah, that's kind of how I feel. Like, what am I supposed to do?
anything like that.
So, I don't know.
research that because I'm sure there's.
So I looked at this problem and I was like, wow, that really looks like a reciprocity formula that I've done before. It just was looking at the form of this going, wow, that looks like reciprocity.
I imagine that Kane will either have some.
Like that's what it reminds me of. So, and I think I have a theory as to why that's true. I don't know.
Probably does also, and it will have pointers.
But other than that, I didn't have any questions on any of this.
So you can look at that, and I'll also try to look for or something like that. But I'm not an expert in that field, so I know a little bit about it, but I don't know what the
Something about the advanced theory.
The one with the young subgroup.
Okay. You know, begin with conversion.
I haven't looked at enough to decide everything down.
I actually had a dream about it last
Like
night.
and with respect to foreigners, is it absolutely necessary or?
Too bad.
Of course they will help, but I mean, my partner said this is a giveaway.
Before the giveaway.
Always.
It is, yeah.
Never won
I want you to do it.
I thought that too much work.
Okay. So
I did,
you might have to
I did
find
number 6 easily. I'm trying to avoid
Yeah, but that shouldn't be
anything
hard.
that requires me to draw something.
There are.
Right.
I know, for example, there's some students in Colombia that just took a class in the algebra.
I know, you must be really pissed off with it. There's a couple of numbers in there.
Yeah, I know, that's
It would
horrible.
be quite possible.
Stop with those numbers.
So I just posted that form.
Yeah.
But,
Yeah, I saw like half of these. We'll give her combinatorics.
And you have any
Yeah.
suggestions?
And actually, there's a professor.
I was kind of like, hey, look, it's a subgroup.
That's
I'll go with
research.
that.
From that point of view,
I don't know what combinatorics is detailed, so I don't.
directions.
I don't know how to
I'll
do
send
that.
an email and
I think I know what a combinatorical proof is. I just don't know how to make it towards
I know what it is. That's what's crazy.
I've seen the combinatorial.
Yeah. That was you.
For example, this is not a combinatorial. So this is actually kind of what I asked you to describe. You can just actually describe all the parabolic motions. So basically, what I want you to tell me is, like, if it's a relation, how can you tell whether it's in here or not? By looking at it, because there is a nice way of saying it. So that's basically what I